Hello, and thank you for joining us on our lecture about Kirchhoff's circuit laws. We'll start with Kirchhoff's voltage law, otherwise known as KVL. The definition of KVL is the sum of all the voltages around any closed loop is zero, where a loop is a closed path through which current can flow. Now if we look at this circuit, this means that with this passive sign convention of plus minus, and the flow of current in this direction, that the sum of these voltages around this loop have to equal to zero. That means that minus Vs will be equal to the value of the voltage dropped across this resistor plus the value of the voltage dropped across this resistor, meaning that when all of these voltages are added together, it will equal zero. Next, we'd like to talk about Kirchhoff's current law, or KCL. KCL is defined as the sum of all currents entering a node is zero, where a node is a point of connection between two or more circuit elements. So in this circuit, we have three nodes. Node A, between the voltage source and the first resistor, node B, that is connecting this resistor with these two resistors in parallel, and node C, which is connecting these two resistors in parallel with the voltage source. Using KCL, we say that all current entering in a node has to exit a node. So that means all the current coming from node A and going into B must also go from B, exit B, into C. So, with this current being I1 from A to B, minus I1 has to equal I2 plus I3, or I1 plus I2 plus I3 must equal zero. Now let's do an example with KVL. We have a 10-volt voltage source and two 5-ohm resistors. Now, choosing the passive sign convention described earlier, with plus, minus, and plus, minus, let's find what voltage is dropped across these resistors. So, in our first loop, we have minus 10 volts plus another voltage, call it V1, must equal zero. This means that V1, or the voltage dropped across this resistor, will be equal to 10 volts. Now, drawing another loop from our voltage source to the far resistor, we will get minus 10 volts plus V2 will equal 0. This means the voltage dropped across this resistor, or V2, will be equal to 10 volts as well. This makes sense because the voltage should be the same across all things in parallel, such as these two resistors and the source, which are all energized at 10 volts. Now let's solve a problem using KCL. In this problem, we're going to use KCL to find this third resistance value. We can start solving this problem by first determining the voltage dropped across this first resistor. We know that voltage is equal to current times resistance. So voltage 1 will equal I1 times resistance 1. It is measured that I1 is equal to 0.1 amp. This means that V1 is equal to 0.1 times 25 ohms. This will leave us with V1 equaling 2.5 volts. Now we can determine the voltage at node B by taking the source voltage of 10 volts and subtracting the 2.5 volts dropped across the first resistor. This leaves us with 7.5 volts. As discussed in a previous lecture, circuit elements in parallel will have the same voltage dropped across them. This means that the 7.5 volts at V will be dropped across both resistors at C. So V2 will equal V3 will equal 7.5 volts. Now we will use KCL to determine R3. KCL states that the current entering node B has to equal the current exiting node B. This means that I1 will equal I2 and I3. We can redefine I1, I2, and I3 in terms of Ohm's law. This means that I1 will be equal to V1 over R1, which will then equal V2 over R2 plus V3 over R3. Filling these in, that will be 2.5 volts over top of 25 ohms will equal 7.5 volts over 100 ohms plus 7.5 volts over our R3 value. Simplifying this will give us 0.1 equals 0.075 plus 7.5 over R3. This will then simplify to 7.5 over R3 is equal to 0.025. Simplifying this again will then give us an R3 value of 7.5 divided by 0.025, which will equal 300 ohms.